Allora, intanto buonasera a tutti, questo è il primo appuntamento con i colloqui della classe di scienze del 2026 e avremo un colloquio su Quantum Computing for Fluids e invito il professor Benzi a introdurre lo speaker di oggi. Intanto grazie per essere qui.
Thank you, Stefano. I'm going to switch to English. I'm honored to be here today to introduce Professor Sauro Succi. Sauro is an old friend of the Scuola Normale, having collaborated here already 20 years ago with the group of Professor Tosi. And more recently, he has taught for 5 consecutive years the course in computational physics in the framework of the PhD program in computational methods and mathematical models. So he has a long, brilliant career, so I will just touch on some highlights. He has a PhD in physics from the École Polytechnique Fédérale de Lausanne after studying nuclear engineering in Bologna. He's held important positions, first at IBM in Rome, then at the Istituto per le Applicazioni del Calcolo, always also in Rome, and since 2018 at the Center for Life, Nano and Neuroscience at the Italian Institute of Technology. He has taught for many years a variety of courses on computational physics, in particular at Harvard. As you can see, he has an affiliation with the physics department, and also, as I mentioned, at the Scuola Normale. Sauro is an internationally renowned expert on a variety of topics, ranging from plasma physics, fluids, especially turbulence, kinetic theory, superfluids, soft matter, especially from a computational and modeling point of view. He's probably best known for his development of the lattice-Boltzmann method, an extremely powerful and widely used technique, originally for fluids, but then it's branched out to cover just about anything imaginable that can be computed, and also for his discovery of extended self-similarity in turbulence. He's the author of about 600 papers and 1 monograph for Oxford University Press on the lattice-Boltzmann equation, which is highly cited as a single author. He has over 42,000 citations on Google Scholars. He's received a number of grants and awards for his research. In particular, he's received several ERC grants, including 1 advanced grant. He's a fellow of the American Physical Society since 1998. He's received the Humboldt Prize for Physics in 2002, the Raman Prize in 2017. He's been a member of Accademia Europea since 2015. He's received the Sigillum Magnum at the University of Bologna and the Eugenio Beltrami Senior Scientist Prize in 2023, and this is just a selection. And last but not least, Sauro is an eager bicycle runner. In fact, he's the son of a famous professional bicycling star, Luciano Succi, who was closely associated with Fausto Coppi. With that, I give the floor to Sauro for his presentation.
Thank you. Thank you indeed. I have some memories of Coppi and Bartali as a kid, but that's another story. I'm not very good at biking, by the way, but anyway. So can you hear me? Because I have to speak a little bit softly because my voice is not in perfect shape. Well, first of all, it's a great pleasure, let alone the honor, to be here today. As Michele reminded you. No, it's my fault. I have to switch it on. Okay, now you can hear me. I was saying it's a great pleasure, let alone the honor, to be here today. Of course, the Scuola Normale is the pride of any Italian scientist, but in my case, I have really a special affection to this institution for the reason that Michele has been mentioning. And it's always a joy to be here. I really mean it. I invariably had a very great time with the colleagues and friends. And this special, when I'm here, I feel like a kid. You know, I look at this room and I feel emotional. So I'm really very, very grateful to Michele, Stefano, and Professor Pimentel for this opportunity. So today we are going to talk about, I will share a few thoughts regarding a topic where I do not have results. I want to make it clear. If you expect me to tell you that quantum computing is going to solve turbulence or little things like this, then you can quit right away, because no. Yet, I'm having a lot of fun. And I will tell you why. So essentially, as I understand, the colloquium is meant for a broad audience of scientists. So I will spend quite a bit of time in just giving the basics of quantum computing. I don't see Vittorio Giovannetti in the room, because otherwise you would fall asleep, because he knows about quantum computing much more than I do. Part 2 is original. That's where, in fact, we spent our basic work for the last couple of years. And in part 3, I will stick my neck out, because this computational metaphysics comes from Walter Kohn, not from me. It's a series of very adventurous thoughts on the borderline of being a crackpot, but I promise I mean seriously. And I hope we can somehow exchange ideas on the value of quantum computing for fluids, regardless of the practical advantage of eventually outdoing classical computers. So let's start with the pedagogical part. Back in 1981, Feynman famously claimed that since nature is quantum, if we want to simulate nature, we better do it on quantum computers. If you dig a little bit deeper, this quadrant here, just to make sure we understand each other, CC means classical computers for classical physics. And then you know the rest, right? CQ means classical computers for quantum, QQ quantum for quantum, and QC is the talk today, quantum for classical. In the end, what Feynman was really referring to, seems to me, I mean, I didn't check with him, unfortunately, is the transition from CQ to QQ. CQ is what Michele does. You solve the many-body Schrödinger equation on a classical computer, at least part of your work, I guess. And as you, for those of you who have been looking into this kind of problem, you know that they have an exponential barrier in the sense that in the Hilbert space of an n-body Schrödinger equation, there is a horrible amount of information, okay? More than you can handle. People, of course, work out methods. After that, we'll come to that at the end. But essentially, Feynman says, if you go to a quantum computer, even if the Hilbert space is so huge, you can compensate for this, because the quantum computer can accommodate much more information, okay? And I would say QQ is the mainstream of quantum computing these days, okay? QC is about, in this plane, is by far the least populated sector, even though I must tell you that it's really growing very, very fast. I spoke recently with Tommaso Calar, who is a major quantum computational scientist hardware-wise, and I told him, look, I choose quantum for classical because I wanted to do something where I have some credential, right? If I talk about fluids, maybe I've done something, and people maybe will listen a little bit to me. But I realized that this is a very sideline, and he said, quite on the contrary, looked like that in this business, many people give for granted that quantum computers will be with us very soon, okay? So they fear that there won't be enough applications for the quantum computers, which to me was a kind of revelation, because I thought, well, it's not so obvious to me that the quantum computer will be with us. But I must say, they're really making fantastic progress. So that's the reason why I decided to go to quantum computer for classical physics. So this is the main motivation. There is a second motivation. When you twist your brain around this task, because it's really brain twisting, you realize that you borrow algorithms from quantum for quantum, but you can send them back. So there is a nice two-way communication from the algorithmic point of view. And much to my delight, at least me, I rediscover quantum mechanics from angles that I never thought about before. Being forced to think, you are forced to think of quantum mechanics in different ways. And particularly, in fact, in the way classical physics emerges from quantum mechanics, and that's the final part. And finally, because it's fun, this is Cabibbo's principle. You know, Cabibbo used to say, why do you do it unless you have fun? Okay, so, and I do have fun. Okay, so I don't know how much time should I spend on that, but I will be very quick. Essentially, the idea is that you know that the Schrödinger equation for a single particle, say you have a quantum oscillator, and there are excited states and ground states. There is, depending on the problem, but in principle, virtually an infinity of discrete states. And the single particle, in a way, is simultaneously partly in each of these states. So once you solve the equation for the wave function, the Schrödinger equation, you are simultaneously evolving an infinite number of energy levels. So there is, in principle, an almost unlimited amount of quantum parallelism by the very fact that the wave function contains all these degrees of freedom altogether. As a matter of fact, when you go to quantum computing for real, generally the qubit is just based on two of these states, ground state and the first excited state, okay? And so the quantum parallelism will emerge in a different way, but this is just a first, somehow, introduction to the fact that the quantum world has a sort of inherent parallelism which is not there in classical physics. And to be a little bit formal, so this is the Schrödinger equation. Formally speaking, this is, you evolve this wave function in Hilbert space. Hilbert space is a virtually infinite dimensional space, an enormous space. And it is, as you take the initial solution, formally is this operator, xiht, simply rotates the state of the system, keeping the norm of the state untouched. So this is in 2 dimensions. You should imagine an hypersphere in n dimensions. And this evolution is called unitary because the norm of this ray should stay untouched. And the quantum computing is basically a way of performing this quantum unitary evolution on actual circuits and quantum gates. There are constraints, and you immediately see that this is a very contrived way of doing computing, because suppose you have to solve, you have to do a square root of a number. How do you cast this into formalism where you can only rotate vectors? I mean, I'm a little bit stretching the idea, but just to give you the flavor. Again, and that would be too long, but on a quantum computer, you cannot clone a quantum state. So that means that you have to do x squared. You cannot do it. Now you get the feel of what brain twisting is, right? And that's also the fun, because you have really to think differently, again, as Feynman at some point advocated, think out of the box. Here you have to think out of the box, because there is no way out. Now, the way, as I was saying, in fact, the basic unit, everybody heard about that, the qubit, the quantum bit, is actually a two-level system. So 0 is the ground state, and you have the first state on top of the ground state, and C0 and C1 are coefficients in front of these two states. These are complex coefficients, but using some symmetry and other conditions, you can easily show that there are only two independent parameters in this representation. And that means that if you take a sphere, which is called the block sphere, the qubit is a point on these spheres, and there are two angles, like in a spherical representation, you have the coordinate, you have a polar angle and theta, and with these two parameters, you characterize your qubit. Now, the very weird thing about qubits is that the system can be, I mean, depending on where you are on the block sphere, there will be a different probability of falling into the North Pole or the South Pole. When you measure the qubit, what you get is a classical qubit. This is a huge minus. It means that, yes, the system can be in any superposition between the ground state and the excited state, okay? But at the end of the day, when you want to extract the information, measure, what you get is a classical. field. And, of course, depending on where you are, there will be a probability of falling into 1 or 0. And that's how, in fact, the quantum computer allows you allows a representation of much larger number of degrees of freedom. So a bit can only be 0 or 1. A qubit can be anywhere. My metaphorical way of explaining is the following. If Michele spends 30% of his time in the United States and 70% in Italy, or me, you know that when he's in the States, he's 100% in the States. A qubit is just having one leg in the States and one in Italy, 30% here and 70% here. That's what the qubit does. Okay? We cannot do that because we are too macroscopic. But, I mean, things are really moving very fast. Just 2 weeks ago, there has been a paper in Nature showing that this 3070 starts to apply to nanoparticles with 10,000 atoms. Big deal. Big deal. Beautiful paper. So this is the famous Schrödinger cat. You all heard the story, right? The cat, you don't know whether the cat is dead or alive until you measure. One of the beauties of quantum computing is that you really work with the cat. The qubit is the Schrödinger cat, and the actual computers are basically a factory of Schrödinger cats, because you really have to deal with these properties. When you measure, it's 0 or 1, but in principle, it can be anywhere. And so you understand that there is an exponential potential advantage in working with the quantum computer as compared to the classical one. But it's potential, okay? And realizing the potential is a very tough cookie. Again, I'm not really the super expert of that. Entanglement, so what is entanglement? Mathematically, to me, the entanglement is easy, but physically, you don't. Let me just give you, again, the bottom line. You have two spins, spinning particles. They are called Alice and Bob in the literature. And no matter what, if you do something on Alice, this will reflect into Bob behavior, no matter how far apart they are, which looks like scientific fiction. Einstein called that spooky action at distance and dismissed that, and Schrödinger himself didn't believe in that. The cat was invented to show how ridiculous it is, and the cat turned it back on Schrödinger, because now the cat is very real. If you are a mathematician, I think it's easy to understand, because you say, I have Alice, which is in A0 and 1. You have Bob, B0, B1. And the composite state, Alice-Bob, if the composite state is a direct product of the two, then they are independent. You can touch Alice without affecting Bob. But in general, the composite state Alice and Bob will have coefficient 0, 0, which is basically the probability that both are in the ground states, 0, 1, 1, 0, 1, 1. And these coefficients are not the direct product of A and B. So mathematically, I have no problem. But physically, you hardly believe that this can happen. And as a matter of fact, it did happen. I think in the last, 10, 15 years, people have definitely shown that these things are real. There was the usual motto by Mermin, I think, shut up and calculate, right? When people were talking about action at distance, entanglement, etc., come on, give me a break. Let's shut up and calculate. Well, No, it was Mermin. I read that it was attributed to Feynman, but it was Mermin. It's Feynman? Okay, thank you for the correction. I read that it's normally attributed to Feynman, but it was Mermin. Anyway, shut up and calculate was the mainstream. I would say no longer so, because these things are real. And I think the hero here, unfortunately, he passed away far too early, John Bell, I know very little about that. So again, I apologize to the experts. But there are things which are really weird. To the best of my knowledge, and again, I'm an amateur here, Bell realized that there are certain quantities, certain correlation. This is the probability that both Alice and Bob measure 0, 0, and the bracket is the average over many. realization, because everything is statistical here. So he constructed this algebraic quantity, 0, 0 plus 0, 1 plus 1, 0 minus AYB1. And by simple argument, you can show that if these are classical probability, that cannot be larger than 2. And he was able to show that there are states, not coincidentally called Bell states, which are entangled, they are not separable. And for those states, the correlation is 2 square root of 2. Much more practically, and don't ask me details, I read that there is a correspondence in game theory. If Alice and Bob are two game players and they are entangled, they can exchange more information than under classical constraints. And there are games where the best classical chance of winning is 3.4. Don't ask me where this number comes from. And you can show that if they are entangled, the probability of winning is higher. So again, this looks like, crackpot. No, nature is like that. Quantum mechanics is like that. And please, please, please do not be fooled. That has nothing to do, so here I'm going back, I want to go. This has nothing to do with superloop for the students. One could say, okay, even if they are far apart, they communicate because there is something traveling faster than the light. No. This is not entanglement is not a physical signal. Entanglement, to me, is a sort of topological property. If the two photons are entangled when they are together, you send them far apart, they remain entangled. So space is out of the game. It's just erased, which is also weird, but again, real. So I think there is a lot of brain twisting in this story, and even at my young age, I have a lot of fun in relearning things that I was not used to, but I mean, for the junior generation, maybe these things are much more natural than for me. Okay, so the entanglement, this is really the basic point, is very, very fragile. And entanglement, of course, any system is coupled to the environment, but this coupling is super strong. Just to give you a number, do you know what is the error rate in our laptop? Any idea? Well, in a class, I would give 3 answers, 10 to minus 3, 10 to minus 5, 10 to minus 20, and ask which is the closest one. This is the colloquium, so I don't ask question. It's 10 to minus 18. So the probability of making an error is 1 billionth of a billion. In the best quantum computers today, it's 10 to minus 3. And that already gives you the idea. You have 15 decades. It's a huge gap to bridge. And yet, people are converging. There are 2 basic directions. And again, I'm not really an expert, but that's the bottom line. On the one side, the quantum physicists, experimental people, they are doing a great job. And they are really improving the resilience of this quantum system to the environment. The other big deal is the softer side, quantum error correction. And again, I can only get the surface of this because everything is very, very detailed, but the point is quite clear. There is a very huge technological challenge, 18 versus 3, 15 decades, but you never know. Maybe tomorrow there will be some discovery of a new quantum state of matter, and you gain, say, 3 decades overnight. That can happen. And quantum error correction is, as far as I can tell, based also on discussion with private companies, is where they're really investing the most of their effort. So it could be, and some people give it for granted, that these 15 orders of magnitude will be bridged soon. And okay, error correction is beautiful. I don't know anything about it, but eventually they can detect where the error is. A spin flip, basically, the error, okay? And you can detect where the spin occurred and eventually turn it back. This is called quantum error correction. Sometimes you can correct. Most often you can only mitigate the error, which means that you can only partially reconstruct the. These are the 2 big mainstreams of quantum computing as we speak, okay? Nothing to do with fluids. How does it work? Beautiful. I mentioned the Hamiltonian, the unitary evolution. Well, the way a quantum computer is built, and you can use it, you can program it and run it, is out of this gate. They are basically spin flippers at the end of the day. okay? Generalized spin flippers. And these gates, X, Y, Z, are rotation on the Bloch spheres, and they're called Pauli gates. And there is a beautiful theorem showing that with a 2-qubit gate, you can basically generate you can do any, it's a universal quantum computer. I think it's an Italian guy, Barenco, I think, among others. They proved this very important theorem. So essentially, this is the quantum basic gates, and the circuit just operates on the qubit based on these gates. This is a real thing. This is a computer that we used that 2 years ago. It's from IBM. And what is it? This is a piece of quantum matter, as a matter of fact. There are 65 qubits, and IBM certifies that you can partition these 65 qubits any way it pleases you, and the two partitions will be entangled. Don't ask me how they did that, because to me it looks like magic. But it's not yet the computer. This is a piece of quantum matter, okay? Now, the computer works like this. You tell the computer what you want to do. So you write down the algorithm first, the circuit second, and then they have a sort of compiler, quote unquote, which maps your instruction into an operational partition, which would be the gates of your circuit, okay? And this, to me, was a great amazement. It reminded me of my days. You know how Lattice Boltzmann was born? I should tell to the young people. I was at IBM, and my boss stepped into my office. He saw a paper where they're using, in those days, quantum cellular automata, which were bits, 0 and 1, and asked me to try that as an exercise to learn the assembler language on the IBM machine. That's how. Just to tell you, life will surprise you. So be always open to weird inputs, because the last thing I would have thought that this would have brought me to Lattice Boltzmann. So this took me back to the days where I learned to program assembler language, which was a lot of fun, by the way, because you really see what your computer, and they even tell you what is the average error rate, depending on what partition you are using. And look, I hope you can see the number. That's what I told you before. The error rate is 10 to minus 2, could be 10 to minus 4. And it's an average number, but far distant from the 10 to minus 18 I was mentioned before. So this is actually what you do if you want to program a quantum computer today. Very, 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 very important. And not something that you find in the main papers. When I first approached this field 2 years ago, I can give you the specific example. I wanted to look into fluids, and I saw a paper, good journal, Nature Computational Science, quantum algorithm for the Navier-Stokes equation. Navier-Stokes equation and the equation of fluids. And I expected to find, solution. You read through the paper, you find a lot of lemmas, complexity estimates, integrals which converge under certain conditions, and then there is a final statement saying, assuming this function is known, and the function is basically the engine of the algorithm, then you can do that and that, but they don't give you the function, right? So just to say that the literature was basically fully focused on showing that you have exponential speed up, etc., but solving the actual problem was not really. And our approach was completely different. So what I want to say is that if you write a circuit, which is a series of gates, and there are layers, right? So basically, they call it volume. I don't know why, because it's an area. Is the width, how many gates you have vertically, and most importantly, the depth. So how many stages in your algorithm. And you are subject to noise, I told you before. So if you have a D level in your algorithm, and you have a P1 probability of making a mistake, by the time you are at the end of the circuit, this will be P power D. So there is a major incentive in keeping your circuit shallow. It's the opposite of machine learning. Deep learning, you want to do shallow circuits, okay? And we were badly hit by that, and I'm going to show that in a minute. Very completely different from electronic computers. There is basically one, all the silicon computers work on a very specific hardware platform. Here the race is still going. There are many different possibilities. These are different platforms. I would say the most important one so far is superconducting electrons, IBM, Google, etc. But there are many contenders. And just recently I had a discussion with these guys, PsiQuantum, just to give you an idea for the young people. This company has of the order of 2.5 billion venture capital. The Italian plan for quantum computing, I think, is expected to be of the order, if everything goes well, 100 million a year. So again, the message, especially to the young, looks like this game is being played by private company. It's a little bit like machine learning. And they are doing, honestly, pretty good work. These are the applications. One wonders why, in fact, so much interest in quantum computing. I don't know. I suspect point 1 and 2 are the most important ones. Because so far, honestly, I don't know of any real application where, in fact, there is the quantum advantage has been really demonstrated concretely. But still, this is what the expert, the forecast. Currently, we are around 4 billion, and they expect by 2030 investments up to 20 billion. So there is a, actually, I've never experienced this. I'm seeing myself. Just to give an example from my daily life, at some point I got a phone call from Volkswagen, okay, and they saw a paper by some Chinese group, and they were willing to put some little money, not much, but nevertheless, it was a surprise to me, just to make an assessment of the Chinese algorithm. That has never happened to me before. The private company calls me to make and is willing to. So just to say that there is an enormous interest, I don't know. I would say that the scientific and the market dimension are kind of interweaved. You cannot disentangle them. So it's not just science. That's what I want to. If we are to trust this, what I tell you is that, in my very small scale, again, I'm experiencing something I've never experienced before, and I keep going the right way, the wrong way. They came to me, and I'm doing something which is really not the mainstream, but what is it? PsiQuantum, I'll come to that. They did just exactly what we did 2 years ago, and they did it better, much to my frustration. And I'll come to that. And Continuum, same thing. So if you do some reasonably good job, and the job gets above the visibility line, they show up. And honestly, that never happened. Yeah, okay. How much do we have?
You have about 20 minutes.
Okay. So anyway, now quantum for fluids, it will be easy. Let me skip a lot, but I think the initial part was important. Why are people excited about the possibility of quantum computing? I think this slide tells the basic point. In fluid dynamics, the basic problem is the turbulence, right? Why do I spend much of time doing, Okay, the Reynolds number is basically the speed of the car times the size of the car divided the molecular viscosity. And this number tells you the strength of nonlinearity in the problem, okay? The reason why fluid dynamics is such a tough cookie is that this number is big. For a car, ordinary car is 10 million, okay? And this is the reason why fluid dynamics is always chasing new algorithms. Now, the complexity, if you have a Reynolds number, given Reynolds number, the number of operations that you have to perform on a computer to solve this flow is Reynolds cube. So that means that for a car, racing car, is of the order 10 to 20, 20, 24, etc. And it's a huge number. So that's the reason why people always look for new algorithms for fluids. And of course, if you go to geophysics or cosmology, it's far more than that. Now, to make a long story short, you can estimate how many qubits do you need to quantum compute a fluid flow with a given Reynolds, and you end up with this simple formula. And here I'm assuming 100 log 10 Reynolds, meaning that if I have Reynolds 10 to 12, which is basically the Reynolds of the global weather forecast system, something that you cannot envisage on any classical computer for many, many decades, this will tell you that with about 1,000 qubits, you would do the job, okay? And 1,000 means, in principle, it would be just 100. 1,000 is 1,000 because I assume that for each actual qubit, there will be 10 doing the error correction. Some people claim that they will need less, and if it is less, it will be 100 qubits will basically allow you to simulate the weather forecast. Big, big deal, okay? But this will be the, let's forget about this. Now, let me go to the specific problems that you have on top of the noise and on top of the problems you have in quantum computing when you do fluids. Quantum mechanics is linear and is unitary, Schrödinger equation. Fluids are neither, typically. So you have two big elephants in the quantum room, nonlinearity and non-unitarity, dissipation. So our work, dissipation, I mean, there are open quantum systems are dissipative, so people had developed algorithms to deal with dissipation, but nonlinearity is entirely new. And there are at least 8 possible, or even more so. People are working at that. Each of them is really beautiful theoretical physics topic. We choose this one, Carleman embedding, and I just want to give some actual original result. Carleman embedding, I can explain Carleman embedding in a very simple way. Suppose you have this equation. I write it as a sort of homogeneous kinetic equation, but it's the logistic equation, okay? There is a quadratic nonlinearity, and that, because there is Rf squared, and as I told you, you cannot compute f squared on a quantum computer because nonlinear operations are not part of the set. So what do you do? It looks like I'm making a joke on you, but no, it's not like this. So this is the original equation. You just rename f, f1, right? And you call f squared, you call f2. So the original equation turns out into the time derivative of f1 minus rf2, which is linear. Nobody can argue against that. Except that it's open because you have to say something about f2. But saying something about f2 is easy because you multiply by f, you get the time derivative of f squared, and you easily show that the tf2 is minus 2f2 minus rf3. So basically, the game is I build an infinite hierarchy. It is formally linear. So I basically transform the nonlinearity away. The price I have to pay is that I have an infinite amount of equation. Is it a good bargain or not? On a classical computer, I don't think so. The Carleman method is not particularly impactful. On a quantum computer, basically, you have no choice. At some point, of course, you have to truncate. And you close your eye, and you hope that by the time you truncate, the error will be reasonable. We did that. And if you have a fluid equation, namely you have a system which evolved in space and time, to make a long story short, you generate a very innocent-looking equation. Time derivative of a vector plus a matrix. It's a linear evolution problem. It looks easy. Except that the size of this problem is huge. G is the number of grid points that you have in your original problem. Nowadays, fluid dynamics, the top is 10 to 12, 1 trillion variables. Say 10 to 9. 10 to 9 is an ordinary fluid dynamics calculation. Each time you go up one level in the Carleman procedure, one level means F1, F2, F3, so you truncate higher and higher. Each time you do that, you get an exponential penalty. So basically, the size of this matrix is the number of grid points in the original points power the level you truncate. So if you truncate the level 2, you get 10 to 18 variables. If you truncate the level 4, you have 10 to 37. And even Michele, who is the top expert in linear algebra. And by the way, quantum computing is linear algebra. I don't want to disappoint you, except that it is linear algebra in 10 to 20, 10 to Avogadro number. And it's a completely, I thought I knew linear algebra. I realized I don't at all. I mean, Michele knows far more. He taught me a lot of things in this couple of days. But really, literally, quantum computing is linear algebra, except that it's in a number of dimensions, which is really challenging all the existing methods. So to make a long story short, I can skip that. So much to my delight, we realized that when we applied this Carleman to my lattice-Boltzmann story, and that's a talk in itself, the convergence is excellent. So we were excited. We do have the algorithm for quantum computers, but then we did the real job, namely try to write the circuit associated to the algorithm.
Can I ask you a simple question?
Of course.
Yeah. Works if k goes to 0 at some point. No? So it works in a region where the variable is less than 1, so that the power
There are constraints on the norm of the and there is another thing that we should talk about. Absolutely, absolutely. And there is the Carleman-Koopman formula. Maybe you heard about it. That is there are. I mean, I choose the powers, but you can have different embedding. And the very beautiful problem, which was brought up to me by this psi-quantum from this. If you have a chaotic regime and you have multiple attractors, maybe Carleman breaks down. I'm not sure they are right, but it's a beautiful theoretical problem. So this idea of somehow, I would say, evaporating nonlinearity and trading for infinite dimension is very fascinating. But I'm afraid they're right. And if they're right, forget about turbulence. It's a beautiful theoretical problem. Anyway, back to the real world. So we wrote down the circuit, not just complexity estimates and the depths of this. The Carleman matrix, to say the long story short, the Carleman matrix that you generate does project on all the Pauli gates I gave you in the beginning. It means that basically the depth of the circuit scales exponentially with the number of qubits. Dead. This was disaster. We were super excited. We have the algorithms. Then when we try to do the real thing, then we realized that quantum computing is a very different story. Okay? So the rest is super technical. It's just like a slalom. You find a barrier, you turn around it, you find another barrier, and it's still not over. That's why I call the call, is it a chimera? Could be a chimera. I mean, I'm not sure we will ever get there. And lately, now this is super technical, but I was very happy to discover that Michele is a super expert. I knew he is a super expert in linear. Sorry, I'm just going the other way around all the time. I want to have 5 minutes for the crackpot part. This is a beautiful problem for the applied mathematicians. Essentially, just to make a really long story short, what we need to do, the only way out I see is, in numerical analysis, you advance time in small steps. You have stability condition, et cetera, et cetera. The trouble is that each time you do one step, you have a probability of failure. Okay? And this probability is unfortunately very high, 10 to minus 3 for one step. In a standard simulation, in standard fluid dynamics, to solve a Reynolds of the order of a car, you need 1 million test steps. So if you have an error of 10 to minus 3 on one step, so we are hoping, but I'm not very optimistic, we are looking for methods to advance our solution in super long steps. It's called telescopic time march. But it should be a factor. The best we could get with a simple diffusion equation was a factor 20. 20 times longer step, we still have a good result. But what we would need, m is the number of classical steps. So if g is 1 billion, it will be 10,000. So it would be at least 2 orders of magnitude, and in fact, much more than that. So I don't. G is the number of grid points. Suppose it's 1, and there is a prefactor, huge prefactor, by the way. So that would be 1,000, 100 prefactor would be 10 to 5 time steps. And you can compute sort of analytically the best you should get to the same solution in about 10 quantum steps. 10 versus, I don't know, I don't want us to say it's doomed, but it's very hard. So just to, I don't want to disappoint you, but because, as I said, you can never rule out the fact that there is a new brilliant idea, and actually, if you believe that there will be computers error-free, without noise, it's called fault-tolerant quantum computing, then you can turn everything into a linear system, and there is an algorithm, in theory, which solves linear systems. Whether it works in practice, it's another story. So just to give you an idea how difficult the problem is, but how fascinating it is. And this is the final, how much do I have? 2 minutes? 3 minutes? Walter Kohn is a Nobel, some 20 years ago. And in his Nobel speech, he said, I believe the Schrödinger equation, the many-body Schrödinger equation, for more than, I think, 10 or 100 particles, is not scientifically legitimate because there is just too much information in this space. Some other people call the Hilbert space a convenient illusion, which I like as a definition. And my point is that so the question is, does the Schrödinger equation, can we trust the Schrödinger equation when n goes, say, to infinity? Or is there maybe some replacement for it? Looks like a philosophical question, but actually it can be very practical. Now, my point is very simple. I have just 2 facts to bring from my own experience. Fact number 1 is that, as I was just telling you, computing classical, nonlinear, dissipative physics in compliance with quantum computing, namely linear and unitary, it's extremely hard, okay? To the point that it could be a chimera. Maybe it turns out to be impossible. I think it will be impossible to build classical computers in a direct simulation. You can do probably other things, but it could be a mission impossible. But the fact, too, is that when you write down this algorithm, this Carleman scheme is a mathematical structure, perfectly serious, no crackpots here. It's an algorithm, very serious algorithm, which computes classical physics in compliance with the principle of quantum computing. Now, you can call me mad or not, but the question, I think, is legitimate. Could it be that there are mathematical structure, I call it QIP as a joke, quantum information patterns? This is what we feel nature does. You have a water faucet, you have Avogadro's numbers of molecules flowing, and we somehow implicitly assume that nature computes the Schrödinger equation in 10 to 23 dimensions because it just has enough power to do it. But we don't. Instead, we have learned that we have a much more economical description, which is the water flow, the Navier-Stokes equation, and that's what we compute on our classical computer. But there might be a pattern in between where nature can still compute in compliance with the quantum mechanics, but even though this Carleman story is much more expensive than a classical computer, it's still astronomically less expensive than solving the Schrödinger equation in 10 to 23 dimensions. So the question is, are these quantum information patterns just a mathematical trick, or could it be that somehow nature makes use of it? And I realize that here I'm kind of crossing the crackpot line. But at least I'm starting from something serious. It's not blah, blah, blah. This is a serious and very hard.
In principle, having something linear and non-unitary could describe an open system, no?
Yes, it is an open system. Yeah. I mean, that would be very long. We believe, the common idea is that nonlinearity and dissipation arise when you project, when you measure. Because the Schrödinger equations, the usual problem, the wave-up function, collapse, et cetera. All I'm saying is that, for sure, this is a fact. There are structures, very well-defined structures, and algorithms which land onto the classical physics, without having the computational complexity of the many-body Schrödinger, and they are still compliant with linearity. And so maybe most likely they're just mathematical artifacts and useless in terms of outdoing classical computer, maybe not. And again, now I discussed fluids, but of course there is a strong interest in quantum computing for PDs in general, okay? There are investments on that, even private companies. I think of biology, but quantum biology is a very, very touchy, you have to be very careful because biology works at standard room temperature and quantum computers usually need to be cooled down to very small temperature. But this is a paper I was referring to, which I find really amazing. So they show entanglement on nanoparticles, which are about 10 nanometers in size, and they find entanglement. I never stumble into that. They call it is an index of macroscopicity. It's basically the ratio between the classical size of the particle and the distance over which entanglement persists long enough. And this is the world record. This 2 weeks ago in Nature. They have this macroscopicity index at 15. The cat is 37. This is 10^2 power, so it's 22 decades. The cat is still, even a Schrödinger rat would be very far apart. But just to say that, I mean, this is serious stuff. This is not crackpot. Beautiful. And don't forget, they entangle about 10,000 atoms, which is basically a virus. Or, I mean, immunoglobulin antibody. So these are real biological aspects. You know that even Penrose advocated that cells would compute as quantum compute, even the brain, and this was ridiculed by people saying, come on, the brain biology is room temperature and entanglement dies at room temperature, which I think still holds as an argument. But nevertheless, showing this kind of experimental result is very remarkable. And then maybe, I mean, that's just wishful thinking, maybe there is some room for new mathematical structures in between the convenient illusion of Hilbert space and the classical solution of nonlinear dissipative systems, which are so hard and may be unbeatable by quantum computers versus classical one. So that's basically the story I wanted to say. So conclusion, is quantum computation fluid dynamics in sight? Not really, in my view. Will it ever be? Unlikely in the way we simulate fluids today, where we really detect all the details, how a vortex detaches, and presumably there will be, will it crack turbulence? I don't think so. But there will be room for hybrid, I think, computing. Namely, quantum computers, for instance, you could do like in machine learning. You could ask a quantum computer as an oracle, say, what is the lift of this airplane at a given time? Just give me this information. Extracting the full information is super costly. If you have n degrees of freedom, it's an n square operation. So the measurements should be minimized. And it will be useful in the sense of developing algorithms which can eventually move back to quantum for quantum. And for what it is worth, it gives a different perspective to the problem of the emergence of classical physics from quantum one from a very concrete computational perspective. So I would bounce back allegation of being crackpot, even though it might be total an illusion, but it's a nice illusion after all. So in the end, the message is, don't shut up, because entanglement, they are real. You can no longer say shut up and calculate. So I would say, don't shut up, but still calculate. Thank you so much for your attention.
Well, thank you. Thank you very much for the fascinating presentation. Are there any questions? sure it works. Maybe it does. It does. Yes.
I was intrigued by what you said about these intermediate systems, because it resonates with other ideas which are common in high energy physics. There's an idea which is called, permeates the field now. It's the idea of an effective field theory.
What?
The idea of an effective field
Effective
theory, which is also what the equations for turbulence are, not that they are not the microscopic equations of the atoms, are some sort of average. So for these systems, truncating a complicated Schrödinger problem by allowing Hamiltonians which are not Hermitian, it sort of has the same flavor of these problems, right? Because
it would be nice to look into some details, because the details matter. Yeah. I mean, I know what effective field theory is in general, but I would not be able to draw a map.
No, but essentially allowing selected non-union, non-Hermitian terms in the Hamiltonian is somehow a way to get rid of some degrees of freedom, which is what you do all the time in physics. When you understand the problem, you reduce the number of degrees of freedom.
Yeah, exactly. I mean, both dissipation and nonlinearity can arise from coarse graining. Yeah.
It's a coarse graining. Exactly.
Yeah. I'm less familiar with the quantum, but let's look into that.
Regarding simulating fluid on a quantum computer, I've seen in your list of the various hardware that you also listed the quantum annealer, D-wave.
Yes.
So since the quantum annealer is basically implementing an easing kind of system, I was wondering whether one could use like the mapping of easing onto gas or lattice to simulate fluids.
Yeah. Well, yeah, that's a very good point. Now, incidentally, I should inform you that there has been a recent announcement called Quantum Alliance, big deal on the journals, and D-Wave and IonQ are apparently putting significant investment into a consortium in northern Italy to give access to their machines to the Italian community, not only the Italian. So I'm somehow involved in that. I still don't understand how, but I know that these things are going on. D-Wave is not regarded as a quantum computer per se, because it's a quantum annealer. And now, just because of this, it is a blame and a blessing, because it's real in the sense that the quantum annealer for problems which can be formulated in terms of annealing algorithm, it works for real, and it does not have these problems of noise, etc. But if you cannot cast your problem into an annealing form, then it's no use. I had discussed this with the Quantum Alliance, and I mean, not that I've been working hard on that, but I couldn't find any simple way of mapping fluid dynamics into a quantum annealer. But many other problems can. Maybe Giorgio Parisi recently is back to his quantum spin models on classical GPUs, and this problem will be perfect for D-Wave. Again, there is beautiful work to be done. You know about QUBO. Okay, QUBO is, what is it? Quadratic, unconstrained, binary optimization. The algorithmic effort is take a problem, try to put it into QUBO form, and then it's perfect for D-Wave. That's a nice pattern. But, you know, I should have said that this story began for me because IIT, my place, they said, well, we want to have an idea of what's going on in quantum computing. Why don't you take a look? Fine, I enjoy that. But now I'm at the point, I didn't tell you the important thing. The Carleman thing, algorithm, I was proud of that because I think the idea of Carlemanizing lattice boson was ours, and people have noticed that, so I was happy. Now they looked into that seriously, and they did something 10 times more extensive than we did, so I'm very frustrated. But no, I'm serious. I told them I'm very jealous because you did a great job. And they put 6 people just on that. And I had a very good postdoc. Good news for you, I had 2 postdocs, thanks to the PNNR, which I think was money well spent in Italy for the quantum computing, I mean, in general. One was immediately hired by Leonardo, And the other was hired by Eni Quantica. You might have heard of that. It's a sub-company by Eni. They want to build their own computer. Massimo Nguscio is there. So, I mean, if you do good work as a young man, you get hired very aggressively. That's not good news for me, because now I have just a single young postdoc, and how can I possibly compete with people who have 2.5 billion? So once Bernie Alder, the inventor of molecular dynamics, they say, once told me, Sauro, it's very simple. If you cannot beat them, just join them. So maybe that's what I should do. Now, what I'm saying is that the matter is very technical. You can have good ideas, you can put them out, but if these people notice the idea, you cannot compete.
Well, you know, not unrelated to what you just said. First of all, I would like to ask you the experimental result that you mentioned at the end. Where is it coming from? Is it a public lab, or is it a private lab?
No. It's a public.
It's a public
I
lab.
can dig out the paper for you.
It's
no,
okay.
This is
public lab.
Open result.
I mean, the reason I ask is the following, right?
Yes.
Physics and market. Okay,
Oh.
you mentioned that, right? And the question is it a novelty, number one? And point number two, is it a safe development? Yeah, well, I stop here.
Yeah. I mean, we are on record, right? We are on air, right, Michele? Because I have to be careful here. Look, I can only give you my, I'm very direct. To me, it's a totally new experience, okay? It's completely new. I just give you an example. I mean, I've been doing so much work with lattice bolts in soft matter, turbulence, etc. Lately, the only, 90% of the invitation I get is for quantum computing, even though I've been always very crystal clear, we do not have the algorithm for the quantum fluids, okay? The reaction is, okay, but it's interesting. So, in this respect, I'm very happy. It's a very nice atmosphere to work. Second thing, the interest of these private companies is real. I think there is a danger there for obvious reasons. But I would not speak of the danger, I speak of my frustration. I'm serious about that. IIT asked me to take a look. I took a look. We did something, I think, reasonable good work. I don't like to run for second place. I mean, I accept that I will end up maybe second, but I want to, at least in principle, be able to end up in the first row. And since there is this strong interest, you realize it's, I think, even more so in machine learning. And this is not my discovery. We know that AI, and in the end, quantum computing as well, the main players are going to be this private company. I'm not sure this is a good thing. On the other hand, I have to say, I had a phone call, I had a Zoom call with Psi-Quantum 2 days ago. They told us about the algorithms that were absolutely open. It looked like an academic collaboration. That's all I can say. But certainly it's something that didn't happen in my generation at all. So for them, it's a different way of doing science. There are good sides and flip sides.
Well, thank you very much. I suggest that we stop here, and if anyone would like to discuss further with Sauro, we'll be around my office. So thank you very much,
Thank
Sauro,
you.
for
Thank
a
you.
fascinating talk. And thanks to all of you for participating.